second example of passive transport was osmosis. And I told you that osmosis was the diffusion of water. But we have to remember what our water molecules look like. And remember, water is a polar molecule. A negative dipole on the oxygen because the electrons are spending more time around the oxygen, and because they spend less time around the hydrogens, we have a positive dipole there. So this means that we have a polar molecule. And I think many of you remember from our sketch of the membrane that we have one part of our membrane that's hydrophilic, meaning it loves water. That's not a problem. But our tails are nonpolar, so they are hydrophobic. They hate water. It's not a party when water's around. So while water has an easy time just hanging out over here around the membrane, it's going to have a very hard time getting through because those tails just do not want it to be in there. That's where we have a very, very helpful tool. I'm going to redraw the membrane. But this time, I'm going to put like this big oval shape after drawing two of my phosphate heads. And I am no good at making three-dimensional drawings, but essentially, what this is a cylinder that goes through the membrane. So if here's our membrane, we have a little cylinder like that. These are protein channels. And our protein channels are going to be very, very specific. Our R groups for our amino acids can be polar or nonpolar. They can also be charged. So maybe one of the amino acids over here, part of the chain is positive, and then we have like a negative, and then a positive, and then a negative, and then a negative. So these protein channels likely have charge. I'm redrawing my water molecule to make it look more simplified. And like we said, the water molecule cannot just pass through the membrane on its own. So when we think about the diffusion of water, we can't just say it's like one of these triangles that's going to pop over. Instead, we need a protein channel. And with this protein channel, water is going to be able to pass through. And the protein channels are very specific because of this charge and their shape to what they allow to pass through them. So this protein channel is only going to allow water to pass through because it starts over here and its dipoles are attracted to this area. There's some more motion. There's a little bit more motion. It gets pushed down further. Now our dipoles are attracted like over here, and then eventually you get a little bit more motion, and you have one happy molecule of water that's over here. So let's edit our definition a little bit. Osmosis is still, yes, diffusion of water. It takes no energy, but it's diffusion of water through a membrane protein. And these membrane proteins that are responsible for allowing water to pass across a membrane, they have a very specific name because it has the letters AQUA or aqua in it. But these proteins are called aquaporins. Aqua meaning water, pore meaning it's a pore in the membrane. Pores are like holes. And the two letters IN oftentimes cue us in to know that something is a protein. So osmosis is the diffusion of water through a membrane protein called an aquaporin. And there's an example of one there. We do have to keep in mind, however, that just like compound X, those triangles that we worked with earlier, water will only move down its concentration gradient. So I'm going to draw a membrane, outside, inside, and blue dots will equal water in this case. There are 2 dots over here and 4 dots, so 4 water molecules over here. We have a concentration gradient because we have more water inside the cell than outside the cell. Eventually, there's some random molecular motion happening. Eventually, though, you'll get a water molecule that crosses over, and so now we have 3 and 3. But the only way that this is going to happen is if you have an aquaporin in your membrane. If you have a membrane without an aquaporin in there, water is not going to be able to move down its concentration gradient because water is polar, and those non-polar tails inside the membrane are very upset by that. So you need aquaporins if you want your water to move across the membrane.